después del tratamiento de una novedosa molécula que se llama tapentadol.
The speaker in the video is Silvia Allende Perez, the head of a public pain clinic in Mexico. She doesn't mention that she's also a former Grünenthal employee.
So on the educational website of Grünenthal in Mexico, we found that a doctor was actually promoting the drug tapentadol as less addictive and as a better drug in comparison to other drugs.
In her presentation, Perez promotes tapentadol and its advantages over other opioids. One of the Grünenthal-branded slides claims the drug's potential for abuse is minimal. The slide also downplays the risk of the drug causing respiratory depression, that is, breathing slowing down to the point of being life-threatening. It claims there were no reports of respiratory depression. But a 2017 study on tapentadol's post-market development concludes that it's actually a major clinical concern with this type of analgesics. The package information also lists respiratory depression as a known side effect. And yet, in 2024, this training video claiming the contrary remained accessible on a platform created by Grünenthal.
So we confronted the company with this video, and actually they took it offline because they said that you're right, this material is not what our scientific research and what our knowledge at the moment is supporting, and this is why they took off this material.
Grünenthal's response to us also acknowledges that some of the slide's claims were incorrect. It says it takes incidents like this seriously and has therefore reviewed all remaining content on the training platform. Grünenthal also commissioned additional studies on tapentadol. It's relatively common in the pharmaceutical industry for companies to fund studies on their own drugs. Before a study or article is published in medical journals, it's usually subject to peer review, meaning independent experts review it anonymously. This process is meant to ensure quality and credibility, and physicians and pharmacists often rely heavily on these publications. But even peer-reviewed publications don't automatically guarantee full independence. Take this article on tapentadol published in the journal CNS Drugs in 2014. At the time, the authors were all Grünenthal employees. The paper claims that the reduced dependence seen with tapentadol might be due to the fact that the drug acts on two separate bodily systems that affect pain. Maria Christoph tells us she and her colleagues showed these studies and articles to experts. Each said they couldn't find any evidence to support these claims. Yet other scientific publications have cited them, which appears to provide additional validation. According to the examination, Grünenthal relied on these studies' results to train its sales representatives to promote the drug. In the United States, Grünenthal initially licensed the marketing rights for tapentadol to Johnson & Johnson. In 2012, J&J was already collaborating with researchers to examine whether the drug's dual mechanism might reduce its risk of causing addiction. In an email to a colleague, one of these researchers wrote, "I don't know of any evidence to support that, but I can live with the people at J&J believing this to be true." To which their colleague replied, "I don't completely get it either." Grünenthal declined to comment on this email exchange. However, the company admits there isn't sufficient evidence to support the claim that tapentadol's dual mechanism reduces its abuse potential. It claims it repeatedly pointed out that the drug's abuse potential is similar to those of other strong opioids. Still, Grünenthal apparently managed to present its new product as a good opioid, or at least as a better one.
So we have on the one hand the strong opioid, the dangerous drug, oxycodone, that is the reason why a lot of people got addicted from opioids in the United States. And on the other hand, we have tapentadol, a drug that actually works quite similar to oxycodone, but is considered a weaker opioid, or at least this is what is in a lot of people's minds. It's a more clean drug, it's less addictive, but this what we found out in the end is not true. Experts we spoke with said it's actually not the scientific research we conducted that is supporting this argument that this drug is less addictive than this drug.
Grünenthal tells us their materials are based exclusively on data from peer-reviewed medical journals, and that whenever that data allowed for comparison to other products, the findings were cited accordingly. But in many countries, Grünenthal's tapentadol has already overtaken generic versions of oxycodone.
Welcome to Go Classes. Or I can say that common attribute, the R1 intersection R2 is 5, and this I can say how to check it. Very simple. All you have to do, just find the intersection. What are the common set of attributes? So if you see the common set of attributes R1 intersection R2, that is empty. There is no common attribute, so that is the reason I can say that because there is no common attribute. So I can say the common attribute is not a super key in R1 or R2, or I can say that common attribute, the R1 intersection R2 is 5, and this can
oxycodone. In Mexico, prescriptions for oxycodone dropped sharply after 2020, while those for tapentadol have increased massively. According to the data collected by the examination, Peru has been spending more and more public money on tapentadol since 2019, significantly more than it did on oxycodone during the entire previous decade. These developments don't automatically mean abuse is rising too. They could even mean that more patients are finally getting access to much-needed pain medication. So far, there's no evidence of widespread, unregulated opioid prescription in Latin America. But what's happened in the United States shows just how quickly markets can shift. Aggressive marketing, downplayed risks, and rising prescription numbers can trigger developments that are extremely difficult to contain down the stretch. Grunenthal argues that strict regulation of their opioids, specifically in Germany, could send a negative signal to other countries, especially to regions already struggling with limited access to opioid painkillers. So let's look at these regions. In some parts of India, reports of tapentadol abuse have been piling up for years. These drugs aren't typically produced by Grunenthal. They're generic versions from local manufacturers. They're often illegally combined with muscle relaxants. During the 2010s, tapentadol appears to have been available in India without the need for a prescription. It wasn't until 2021 that India's health ministry began responding to growing abuse of the drug. But the most devastating consequences can be seen in Africa. Parts of the continent have been dealing with a severe opioid crisis for years now.
Tramadol is highly abused in many African countries, especially in Western Africa.
To swap functionality. Now this video is for Chris. He is a subscriber here on YouTube. On this. But this now all 2-button styluses have differently. This click button for that. Shortcut control. So here we're going to just keyboard shortcut control / if you don't have this installed, the link is in the description. Okay, what we're going to do is we are going to go to, we're in input mode already, we're going to go to advanced. This menu right here, if you have the pen tool installed, you can just single click. The eraser will open up this panel right here. So those are the 2 ways to get to it. And what we're going to do is we're going to drag from this locate button over here to the orange stylus. And the second one, we're going to drag to the eraser.
This plant is commonly known as the African peach. In Cameroon, it's used to treat ailments like pain, malaria, and fever. A team of Cameroonian and French researchers wants to find out what exactly gives this plant its supposedly analgesic properties. They end up finding an active ingredient in the root bark. When they analyze it, they can't believe their eyes. In medicine, this exact structure is known as tramadol. The compound they've just found in the plant is chemically identical to the opioid Grunitol developed in a lab decades ago. Up until now, tramadol has been considered a fully synthetic, man-made drug. Can this really be true? To make sure, the researchers examined plants from 3 different places in Cameroon, collected during different seasons. They find tramadol in every single sample. By now, they've ruled out accidental contamination. They're sure the substance must be of natural origin. Their discovery makes headlines around the world. Now they want to understand how exactly the plant is able to biologically synthesize tramadol, but they'll never get the chance. A year later, this study is published. 4 other researchers debunked the allegedly groundbreaking find. The tramadol found in the African peach clearly doesn't have a natural origin. It's man-made. The team also finds the synthetic opioid in other plants, in soil samples, and inside well water. Some of the water samples reveal alarmingly high concentrations. Tramadol has made its way into the groundwater. Cameroon isn't the only African country affected. Many people in Togo, Nigeria, Ghana, and Egypt have also become dependent on tramadol. According to the United Nations, non-medical use of tramadol has been a growing problem on the continent since at least 2013. Some African countries are facing full-blown opioid crises. Zico works as a moto-taxi driver in Lomé, the capital of Togo.
Quand il y a embouteillage, c'est nous. On faufile dans les voitures et vite, on va te déposer. Je travaille 12 heures de temps. C'est que je commence à 6 heures du matin, ça fatigue trop.
He describes his experience in this fantastic documentary. He came to the city to make money. He and his colleagues live on the street, and they're addicted to tramadol.
Le tous vont prendre ça. Si tu as pris ta dose, ça va te faire du bien, tu vas bien travailler. Mais si tu as abusé, c'est le truc même qui va te contrôler. Et ça va te créer des problèmes.
Zico uses tramadol to get through his 12-hour shifts and the rest of the day. He takes about 2 pills a day. But the tramadol he consumes doesn't come from Grunitol. The company tells us it doesn't distribute tramadol in West Africa. Instead, the market is flooded with cheap generic versions illegally trafficked from China and India. And counterfeits, which often contain higher or lower doses than their packages suggest. Some contain no tramadol at all. Zico doesn't need an expensive printer to get his pills. Tramadol is everywhere. Users can buy it in pharmacies, at roadside stalls, or on the black market. As the original developer of tramadol, Grunitol may be morally responsible for what's happening in these African countries, but only indirectly. At the same time, the company has obviously been lobbying against stricter regulation, especially in Germany. Remember its claim that the regulation would send a fatal signal to the rest of the world. That doesn't sound coherent to us.
But this is the argument that also the company was spreading. So in my opinion, and what experts told us, this has no direct connection. You care about the people in Germany, and you have to take care that people don't get addicted. In African countries, there's other regulations and there's other possibility to have a safe environment. But this is what they say and what they put in the mind of people.
Maybe Grünenthal was worried that regulating the product more strictly in its original market could send an entirely different signal, namely that the drug is more harmful than the company's been marketing it as for decades.
I think with having this in mind, it's hard to take all of the responsibility away from the company because, it happened that people thought this is less addictive. But in the end, it's the same opioid as other opioids, and all opioids have the potential to get people dependent.
Grünenthal doesn't deny that opioid painkillers like tramadol can be misused and cause addiction. Here's what it does say. It doesn't market tramadol as a drug with low risk of abuse or dependence. Its position on the product's abuse potential was based on scientific data that was always shared with regulators. Tramadol should only ever be used under strict medical supervision and following careful risk-benefit assessments. Regulating its legal medical use ultimately fell within the purview of national governments. The company supports stricter measures if the situation within a certain country requires them. But in several West African countries, tramadol was only regulated more strictly after the drug had already been wreaking havoc for years. Pharma is a trillion-dollar industry. The global pharmaceutical market has been growing for the last 2 decades and is now worth almost $1.7 trillion. That's partly because societies around the world are getting older. To sell their products, some companies still rely on proven methods. But highly addictive drugs like opioids should deliver on their promises from the very beginning. From addiction and social decay to lethal overdoses, many substances that can save lives also have the potential to destroy them. Pharmaceutical companies are at least partly responsible for how openly, honestly, and adequately societies handle the risks tied to their drugs. But where does their responsibility end? With patients who believe they won't become addicted to a certain opioid? With countries where the active ingredient they developed is spiraling out of control? Or with young people who experiment with drugs and suddenly find themselves heavily addicted because they can easily get the pills and underestimate the risks? Grünenthal tells us it's committed to the responsible use of opioid painkillers. Their targeted effects remain essential for patients suffering from severe pain, like cancer patients and people recovering from major surgery or serious injury. The company says that opioids are the last option available to many people's doctors. At the same time, it says it no longer plans to research and develop new opioid drugs. In 2024, sales of Palexia and Tramol accounted for a low double-digit percentage of Grünenthal's total revenue. And the company expects that share to continue shrinking in the years ahead. Strong medications have always been abused, from morphine and heroin all the way to fentanyl. That's precisely why governments and regulatory agencies carry so much responsibility. They need to recognize dangerous developments early on, respond quickly, and regulate accordingly. Decisions about medications must remain independent. They should always serve the interests of patients, not the interests of pharmaceutical corporations.
Of course, we were always thinking, has this company learned from its dark past? And I would say, on the one hand, yes, they definitely tried to change something. They also had a working group that was actually reviewing documents if they are still in line with the latest research. On the other hand, what we found is that all this influence, all this money that actually flows to these organizations and to doctors and to scientific research is another way of influencing and potentially also harming people who get this opioid prescribed, thinking it's less addictive. So this is just probably also another way of having a bad influence. And what I have to say is that the whole image of creating a world without pain is something that is quite misleading, because a world without pain doesn't exist, and especially an opioid is not changing this world where pain actually exists.
Our sun gives the Earth the heat and energy that we need to survive. but it's a little bit boring, right? So I think we should kick it up a notch and replace it with the craziest, most extreme objects ever found in the universe and see if Earth can survive. What if the replacement is more massive, more violent, or even more alien? Let's go through.
Over the years, I've turned many things into alcohol, like toilet paper and children's glue, and now what I want to do next is turn air into alcohol. This is actually something that I first started thinking about all the way back in 2019 when I realized that air technically contains everything that's needed to make drinkable alcohol. I mean, it of course doesn't have the typical alcohol-making ingredients like sugar and yeast, but it does have water vapor as well as CO2 gas, which is theoretically more than enough. This is because together they contain the elements carbon, hydrogen, and oxygen, and with a bit of chemistry, it should be possible to break them apart and to then build them into a molecule of alcohol, or more specifically ethanol. At the time, I also kind of became obsessed with this idea, and I really wanted to try it myself, and for some reason, I didn't think that it would be too difficult. With just a bit of research though, I quickly realized that I was completely delusional, and that it would in fact be the hardest thing that I'd ever attempted. For example, not only would I apparently have to build an entire gas reactor system from scratch, I would also apparently have to fill it with my own custom-made catalyst and then run it at a legitimately dangerous temperature and pressure, and when I saw this, I kind of just gave up on the idea. However, over the years, as I worked on other projects where I made things like purple gold, superconductors, and even my own liquid nitrogen, I slowly gained more and more experience. Then at some point, I eventually felt that making air alcohol was something that I might actually be able to do, and at the same time, I was really curious to know what it would taste like, and well, I figured there was only one way to find out. With that being said, I then just went ahead and got started, and I felt that the best first step was to put together some sort of plan. So that was what I attempted to do, and after thinking about it for a while, this was what I eventually came up with. To start, I would pull water vapor and CO2 from the air, then I would electrolyze the water to make hydrogen gas, which I could then combine with the CO2 and pass as a mixture over a catalyst, and ideally, this would produce some nice and drinkable ethanol. I mean, this was all of course just a very general plan, but it at least gave me an idea of what I was gonna have to do, and I just went ahead and got started by first trying to get the air water and the air CO2. I also felt that the water would be the easiest to get, so that was what I decided to go for first, and I figured that all I had to do was buy a generic home dehumidifier and then run it. So that was exactly what I did, and for the most part, it was as easy as I expected, and I basically just let it sit there, pulling moisture from the air and dumping all of the water into this large beaker. There was one sad and kind of pathetic thing about this whole process though, which was that I was actually doing all of this in the middle of winter when humidity was already really low. So the process quickly became painfully slow, and it only got slower and slower as it squeezed out the very little water that was even there. This in turn also caused the humidity in my lab to just keep getting lower and lower, and nearly a month later, when I finally had the 1600 mils that I wanted, my lab was so dry that it might have actually been bad for my health. But either way, with all of that thankfully done and over with, I just took all of this nasty air water and I quickly cleaned it up by first pouring all of it into a cheap water boiler. I then added the top part along with a beaker, and after turning on the power, it wasn't long before some nice pure air water started distilling over, and I waited for it all to eventually make it. Then after that, I transferred all of this beautiful air juice to a nice glass bottle, and for the time being, I temporarily put it aside, because what I had to do now was move on to the other main ingredient, which was the CO2. For the CO2 though, I knew that it was going to be a lot more difficult to get than the water, and this was mostly because A, there just isn't that much CO2 in the air to even extract, and B, selectively pulling it out and isolating it is not nearly as straightforward. However, after doing a lot of research into every single CO2 capture method that I was able to find, I eventually came up with a decent plan that I felt would work. I then almost immediately got started with it by first getting my huge container of generic sodium hydroxide drain cleaner and by pouring a bunch of it into a large glass dish. Then, after spreading it out and making it as even as possible, I just let it sit there and I waited for it to start pulling moisture from the air. It also shouldn't have had a problem doing this because sodium hydroxide is extremely hygroscopic, and I was very happy when it only took a couple of days for the entire thing to liquefy into a goopy mess. At this point though, I should say that waiting for all of the water to come from the air was mostly just out of convenience, and I definitely could have added it myself. But regardless of that, what I had now was an extremely concentrated soup of sodium hydroxide, and at least in theory, it should have been able to do something very important, which was slowly absorb CO2 from the air. What I mean by this is that as it just sat there, CO2 in the air should have been slowly and passively dissolving into the water and then almost immediately reacting with the sodium hydroxide to form sodium carbonate. This in turn should have caused there to be a constant flux of CO2 coming in and getting converted to sodium carbonate, and basically, this liquid should have been able to continually suck CO2 from the air. The very important trick here though was that none of this CO2 was truly being destroyed, and it could all be easily released from the sodium carbonate whenever I needed it, and this will all make a lot more sense later on. But with that being said, I then just let it sit there and I occasionally stirred it, and as more CO2 was captured, more sodium carbonate formed, and it was all supposed to slowly solidify. The only unfortunate part was that just like getting the water, this whole process ended up being excruciatingly slow, and after a couple weeks, I genuinely started worrying that it was never going to be done. However, that thankfully wasn't the case because over the next 2 weeks, it did slowly dry up, and eventually, I was left with some nice and crispy sounding sodium carbonate, which was exactly what I was hoping for. At this point, I was also very relieved to finally be done with this horribly inefficient process, and I was pretty happy with how much I seemed to have made because it was quite a bit, and it was apparently about 2,100 grams. This in turn meant that I'd potentially captured around 850 grams or about 2 pounds of CO2 from the air, which I felt was kind of impressive, and as far as I could tell, this was more than enough for the entire project. But anyway, with all of this powder and air water now in hand, I was ready to move on to the next step, which was to figure out exactly how I was going to be using this stuff to make the ethanol. I mean, I knew that I was going to be electrolyzing the water to make hydrogen gas and using the sodium carbonate to make CO2, and then combining and reacting these gases over a special ethanol making catalyst. But that was just a very simplified plan, and as I mentioned earlier, to actually do this in real life, it would be way more complicated, and it was going to require things like an entire gas reactor system and a very special catalyst. I was also going to have to make all of this myself because both of these things were basically impossible to buy and they had to be fully custom, and this was quite daunting to say the least. For some reason though, I still had faith that I could do it, and from what I could tell, it seemed like putting together the reactor system was going to be a little less painful than making the catalyst. So I decided to focus on that first, and I ended up spending the next few weeks just doing research and trying to figure out how high temperature and high pressure reactor systems even worked. Then, when I felt that I had a decent idea, I moved on to the next very important part, which was to put together my own design, and this turned out to be quite difficult for many reasons. However, the main one was that whatever I came up with had to be fully compatible with hydrogen gas, which was not only extremely flammable and potentially explosive, it was also capable of something called embrittlement. What I mean by this is that since hydrogen is such a small element, it's actually able to diffuse into many metals and to slip in between the spaces of their atoms. This in turn can cause the metal to become brittle and to potentially break catastrophically, which is especially dangerous when working at a high temperature and pressure. And the scariest part is that there is technically no way to fully prevent this, but there are some alloys like brass and 316 stainless steel, which are much more resistant. So that's what I was going to have to use to build the system, and at the same time, I was going to have to make sure that all of the internal parts of every piece were compatible with hydrogen as well. Also, on top of that, there was one other major thing that I had to consider, which was that this process would produce a decent amount of extremely toxic carbon monoxide, and I would of course have to safely deal with that. With all of this in mind though, I did eventually put together a design that I felt would work, and I spent the next few months just buying all of the things that I was gonna need. For example, I got a bunch of stuff like some gas cylinders and something called a gas booster, as well as some two-stage regulators and a hydrogen generator, and a lot of other random parts and pieces. Then, when I eventually had everything, I started putting it all together, and well, long story short, it turned out that my initial design kind of sucked, and I ended up running into at least a few critical issues. I also ended up spending a ridiculous amount of time dealing with what felt like a never-ending stream of little problems that just kept popping up, and I definitely bought way too many things in my sad struggle to fix them. But I guess this all should have been kind of expected, because I wasn't exactly an expert with any of this, and this was by far the most complicated thing that I had ever attempted. After several painful weeks though, I finally had something that I was reasonably confident would work, and I went ahead and built an entire wall behind it just to give it a nice white background. Then, with all of that in place, this was the final result, and in my opinion, it was one of the coolest and most impressive things that I had ever built. It was also a lot simpler looking than I ever thought it would be, and this was mostly because I spent a long time trying to make sure that it would be nice and presentable. But either way, overall, I was very happy with how it all turned out, and I was really excited to actually use it, except unfortunately, that wasn't something I'd be able to do for a while. This was because at this point, there was, of course, one extremely important thing that I still had to do, which was to make the special ethanol-producing catalyst and to load it into the reactor over here. So that was, of course, what I was going to have to do next, and I just went ahead and got started with it by first doing a bit more research to try and figure out exactly which catalyst I was going to be making. I then spent a very long time analyzing the ridiculous number of options that I ended up finding, and I attempted to single out what I felt would be the best one, except long story short, it turned out that they were all kind of bad. What I mean by this is that in general, none of them were very efficient, and on top of that, a lot of them had some other major downsides, like being extremely expensive or very difficult to make, or even a combination of the two. This also unfortunately wasn't too surprising, especially considering that even now, the direct conversion of hydrogen and CO2 to ethanol is still a relatively new field of research. That said, I did eventually stumble onto this paper, which I thought looked super promising, because the catalyst that they made seemed to be exactly what I was looking for. And by that, I mean that it was one of the most efficient ones that I was able to find, and on top of that, it was relatively inexpensive. The only slight catch was that it was a two-part catalyst with a so-called CZA portion as well as an iron-based portion, which meant that it would be a bit more complicated to make. However, after reaching out to the first author of the paper and asking a bunch of questions, I was pretty confident that it wouldn't be too bad. So I kind of just decided to go for it, and at the same time, I figured that the best place to start was with the iron-based portion of the catalyst. This was because, at least based on the procedure in the paper, it seemed like it was going to be the hardest part, and I liked the idea of dealing with it first, and after going over things a few times, I found that there were going to be 3 major steps. The first was to make something called an iron metal organic framework, or iron MOF for short. The second was to basically burn it and to turn it into something the paper referred to as iron at carbon, and then the third was to coat this with sodium ions to make the final catalyst, called 2% sodium iron at carbon. Overall, I had to admit that altogether this did sound like a lot of work, especially considering that I was going to be massively scaling up the original procedure, but at the same time, I still didn't feel like it would be too bad. So I just went ahead and got started with it by first getting a flask and by adding 300 ml of a solvent called dimethylformamide, or DMF for short. Then into this, I quickly added 3.6 grams of iron chloride tetrahydrate, which almost immediately started dissolving and forming some nice colored complexes with the DMF, and after letting it sit there for a bit, I turned on the stirring. This caused the solution to quickly become an even darker orange and for it to slowly get darker and darker, and once it had completely dissolved, I quickly added the next ingredient, which was something called triethylene diamine, also known as DABCO. Like the iron chloride, this caused a nice and strong color change, and what should have been happening here was a reaction between the DMF iron chloride complexes that I just made and the DABCO. As far as I know, this was leading to the formation of a bunch of different intermediates, where the major one was probably some so-called hydroxo iron species. It was going to take at least a few minutes for it to all react though, so in the meantime, I went and got my addition funnel, and I added it to the top of the flask. With that in place, I was then able to add a nice and clear solution that I'd made by dissolving a small amount of terephthalic acid in about 70 ml of DMF, and when I was done with that, I looked back at the reaction and it seemed good to go, so I carefully opened the funnel. This caused the solution to be let out really slowly, and my goal was to add it all dropwise, and this time, there wasn't an immediate color change or anything. In theory though, the terephthalic acid was supposed to be reacting with my mixture of random intermediates and leading to the formation of a new complex that's generally referred to as an Fe3O trimer. However, these trimers wouldn't stay on their own for very long because they were all supposed to continue reacting with the terephthalic acid to form intermediate molecules that could then combine with each other. This in turn was supposed to lead to the formation of a massive and highly ordered structure that would be held together by strong bonds between the iron and terephthalic acid, and in general, this is known as a metal organic framework, or MOF for short. But anyway, once it was all added, I transferred it all to a Teflon container, and after sealing it, I dropped the entire thing into a large stainless steel pressure chamber. This was because most of the reaction that I just mentioned wasn't really going to be able to happen at room temperature, and in order to actually make the MOF and to have it form with the proper crystalline structure, I was going to have to heat it up under pressure. So that was exactly what I did by just putting the entire thing in my oven that I had preheated to 120°C, and after leaving it there for about 24 hours, I took it all apart and I pulled out the Teflon container. I then quickly popped it open, and the first thing that I noticed was that the color was way brighter than before. And in my opinion, it kind of just looked like some generic paint. But as far as I could tell, this was exactly what I was looking for, and what I had now should have been just a bunch of MOF floating around in a soup of DMF, along with a bunch of other random side products. I of course only wanted the MOF though, and the rest of the stuff was just trash, so what I was gonna have to do next was purify it out, and I was honestly a bit worried that this was gonna be a huge pain. But despite that, I just went ahead and got started, and well, for the most part, it actually ended up being relatively simple. And by that, I mean that basically all I ended up doing was just centrifuging it to push all of the MOF to the bottom of the container, which allowed me to easily get rid of the dirty DMF. Then after that, I was able to clean it up even more by washing it with some fresh DMF and by using the centrifuge again to knock everything to the bottom. I also ended up repeating this cycle a few more times just to really make sure that it was all clean, and when I was eventually done with that, I put it all into my vacuum oven. This was because I wanted to get rid of any remaining DMF and to dry it as much as possible, and a few days later, this was what I was eventually left with. Just a nice pile of dry and crunchy powder, which should have been nearly pure, iron-based MOF, and with this now in hand, I was feeling pretty good. At this point, I was also officially done step 1 of this catalyst, and I could now move on to step 2, which was to basically burn everything that I had just made and to turn it into iron at carbon. So that was what I immediately started working on next, and the first thing that I did was quickly put together this little setup, where over here I had a high purity nitrogen tank that would allow me to flow nitrogen gas out of this black tube and into this flow meter, and then into this tube furnace. At the same time, I also had this vacuum pump that was connected to the same end of the tube furnace, and this will all hopefully make a lot more sense in a few minutes. But with that being said, I then just got started with things by first transferring all of my powder to an alumina boat. I then slid it into the quartz tube that was sitting inside the tube furnace, and after loading in another alumina plug and sealing the open end, I flipped on my vacuum pump. This caused all of the air in the tube to get sucked out, and once I saw that I had a nice stable vacuum, I closed the valve to the pump, and I refilled the tube with some high purity nitrogen gas. Then, after repeating this process 2 more times, just to make sure that there was only nitrogen in there and effectively no oxygen, I opened the valve on the end of the tube so that nitrogen could flow through it, and I carefully adjusted the flow rate to 500 mils a minute. With all of that done though, it basically should have been good to go, and at this point, I was feeling pretty good about things. So I just went ahead and flipped on the heating to start the whole cooking process, and the goal now was to slowly raise the temperature at a nice and steady rate of only 2 degrees per minute. It was also going to have to go all the way up to 550 C, which meant that this was going to take a while, and for the first couple of hours, not too much happened. However, when it eventually got to around 200 C, I started to see some smoke coming out with the nitrogen, and as it continued getting hotter and hotter, it slowly got smokier and smokier. Then, by the time that it got to 450 C, it was just blasting out, which I thought was pretty satisfying to see, and as far as I could tell, this was exactly what I wanted. It also told me that everything that I'd put in the tube was definitely breaking down, which was good, except I should probably say that all of this stuff blasting out technically wasn't smoke, and that nothing in there was actually burning. This was because with no oxygen present, it would be impossible to burn, and instead, it all should have been gently breaking down through a process called pyrolysis. More specifically, the moth should have been slowly decomposing and turning into gases like carbon monoxide, hydrogen, methane, and CO2, which was all getting carried out of the tube by the nitrogen. Left behind, though, would hopefully be a bunch of carbon in the form of charcoal, which is basically the stuff that's found at the bottom of a fire, and this probably doesn't sound too special. But in this case, it would be, because it would all be coming from the iron-based moth, which has a unique and highly ordered structure with a very specific arrangement of iron atoms. This in turn was supposed to result in a highly porous charcoal that was filled with an extremely even dispersion of iron-based nanoparticles, and this was what the paper referred to as iron at carbon. But anyway, as it continued getting hotter, the amount of smoke gradually got less and less, and by the time that it got to my target temperature of 550 C, there was barely any coming out. Then, as I continued heating it, the smoke only continued to decrease, until a few hours later when it eventually stopped coming out at all, and at this point, everything in there should have been fully degraded. So what I did next was just turn off the heating, and I waited for the entire oven to cool down, and when it eventually got to a reasonably low temperature, I just went ahead and opened it up. What I then saw was that everything had become completely black, which was exactly what I wanted, and it was definitely very different than the nice salmon-colored stuff that I'd put in. As far as I could tell, it also looked like it had been fully carbonized, meaning that what I had now should have been just a bunch of carbon filled with a fine dispersion of iron nanoparticles, and overall, I was pretty happy with how it all turned out. The only slightly concerning part was that upon closer inspection, I did notice that there was actually some red color in a few places, which at first, I thought might have been some stuff that didn't break down. Then on top of that, I also noticed that everything that I had was actually brown and not black, like pure carbon should have been. However, after looking back at the paper, I quickly realized that this made a lot of sense, because it clearly stated that a lot of the iron was supposed to be turning into iron 2 oxide, which is brown. Also, for the small amount of red stuff, I came to the conclusion that it was likely just due to a bit of oxygen contamination, and as far as I could tell, it was all just superficial, and it wasn't going to be an issue. But regardless of that, at this point, step 2 was now done, and with only one step left, I was already getting really close to having my finished iron-based catalyst, and so far, I had basically run into no real problems. I mean, that wasn't until I weighed it, and I saw that what I had made was only 1.8 grams, which was way less than I ever imagined I would get from this, especially because I had already scaled up this reaction by 6 times. The final step wasn't going to add any real mass to this either, which meant that 1.8 grams was the max that I was going to get, and this was more than just a little concerning. This was because, based on my calculations, I was going to need at least 25 grams of it to make ethanol at a decent rate, and to get that, I would apparently have to repeat the entire process 13 more times. And considering that what I had just done had taken about 5 days, I was potentially looking at up to 65 days of work. Just thinking about that kind of hurt my head though, and at this point, I was extremely tempted to just quit on this catalyst. However, at the same time, I still felt that there was some hope, and after thinking about it for a bit, I was pretty convinced that all I had to do to get through this was just scale things up even more. From what I could tell, there was also only one major bottleneck that was stopping me from doing this, which was the stainless steel pressure chamber, and it seemed like all I had to do was buy a massive one. So I just hopped onto Alibaba, and after searching around for a bit, I ended up buying this one, which was the biggest one that I could get before the price skyrocketed and became completely unreasonable. Then, when it eventually arrived a few weeks later, I just jumped right back into things, by basically doing the exact same process all over again, except on a much bigger scale. At the beginning, everything also seemed to go totally fine, and with step 1, the only issues that I ran into were some slightly annoying things. Like the fact that the new reactor was way heavier than the other one, and once it was loaded up with the entire reaction mixture, it weighed around 80 pounds. This made it a pretty painful process to get it both in and out of the oven, and to move it around in general, and I even had to reinforce the rails in the oven to prevent them from breaking. On top of that, having to deal with so much more product made the centrifuging and cleaning steps a lot more tedious, and I ended up having to get my Rotovap going just to deal with all of the extra solvent. However, all of that turned out to be very pleasant compared to what came next with step 2, when I realized that I'd somehow completely forgotten that I could only load one boat at a time into my tube furnace. This meant that the whole process still had one major bottleneck, and I have no idea how this completely slipped my mind. Regardless of that though, I ended up deciding to just power through it instead of trying to buy a bigger tube furnace or something, and let's just say that it was pretty painful. This was because with one boat at a time, I ended up having to repeat the process 14 times, and considering that each run took a full day, this was basically all I did for 2 weeks. What also made things extra fun was that at the same time, I had to keep repeating step 1 so that I would have MOFs ready to continually load into the oven, and pretty much the entire time that I was doing this, I was kind of wishing that I had just given up. But either way, in the end, when I did eventually finish, the final result was 4 separate jars with about 6 grams of iron at carbon in each one, and at this point, I was honestly so beyond done with this process. However, on the bright side, in total, I somehow ended up with exactly 25 grams, which was suspiciously convenient, and now with step 2 officially completed, I was super close to finally being done with this catalyst. As far as I could tell, it also seemed like the last step was actually going to be really easy, because I just had to add some sodium ions to what I already had, and according to the paper, all I had to do was a process called wetness impregnation. The only slightly tricky part was that I'd honestly never heard of that before, and when I googled it, I was only able to find very general information about it, but not exactly how to do it. After looking around forever though, and watching every random video that I could find, I eventually felt that I knew how to do it myself. So I just went ahead and got started by getting that first small batch that I'd made and by dumping it all into a bowl. And on top of this, I quickly added all of the stuff that I had in the jars, which altogether now gave me a total of 26.8 grams, and after stirring it around a lot to make sure that it was fully mixed, I transferred a small amount of it to a dish. I then very slowly and dropwise started adding a solution of ethanol in water, and the goal here was pretty simple. All I had to do was carefully add the solution with a lot of mixing in between the additions, and to go just until the point that it started clumping. Because at this point, it would mean that the powder was at its limit of what it could absorb, and when I eventually saw this happening, I wrote down exactly how much liquid was used. Then after that, I repeated this 2 more times, with each run giving me a ratio of liquid to powder, and after averaging things, I found that the ideal quantity was 1 milliliter of liquid to 0.293 grams of the catalyst. With this in mind, I was also able to calculate that I would need exactly 87 milliliters of the ethanol solution to perfectly coat all of the catalyst that was still in the bowl, and I added that amount to the beaker. Then into this, I added 1.16 grams of sodium carbonate, which would serve as my source of sodium ions, and once it all eventually dissolved, I went back over to the powder, and I quickly ground it to a dust. I then started to dropwise add the solution that I had just made, with a lot of stirring in between, and the goal now was to basically add everything, and to coat the catalyst as evenly as possible. The key here though was that in doing so, all of the sodium carbonate that I had added would get perfectly distributed throughout the powder. I'd also specifically used 1.16 grams of the sodium carbonate because I had calculated that this was exactly how much I would need to get a final catalyst that was 2% sodium by weight, which, according to the paper, was the ideal amount. But anyway, when I was eventually done, it was looking a bit more wet than I would have liked, except I felt that this was fine, and I quickly dried it by putting it in my vacuum oven. Then, when I took it out a few days later, what I had was a super nice and dark powder, which in theory was the 2% sodium iron at carbon catalyst that I was hoping for, and now, after working on it for nearly 4 months, I was finally done. At this point, I was also so beyond tired of this catalyst, and this project in general, that I ended up working on some other stuff for a week, just to clear my mind. After that, though, I felt that I was ready to jump back into things and to make the second catalyst, which at least initially seemed like it was going to be roughly 1,000 times easier. Because as far as I could tell, the whole process was somewhat similar, except way more straightforward, and the basic idea was to first make the so-called CZA precursor, then roast it to make the proper CZA catalyst, and then after that, add some potassium ions to make the final 5% potassium CZA. The only slightly tricky part was that for some reason, the procedure in the paper was missing some fundamental key details like concentrations and amounts, which definitely wasn't ideal. However, after doing a lot of research and after reading every single similar procedure that I could find, I was eventually able to come up with my own numbers, and I was at least pretty sure they would work. So, with these numbers in mind, I just went ahead and got started by first adding a bit over half a liter of distilled water to a large beaker, followed by 71.04 grams of copper nitrate. This almost immediately caused a lot of the water to turn a really nice blue color, and I quickly followed this up with 35.1 grams of zinc nitrate and 22.06 grams of aluminum nitrate. With all of these nitrate salts added, I then turned on the stirring to help dissolve everything, and when it all eventually disappeared, I dumped in the last ingredient, which was urea, and I added 180.18 grams. Just like all of the other stuff that I had added, this also dissolved relatively quickly, and when it was all eventually gone, I poured in some more water to bring it up to 2 liters. This then finally left me with a nice blue solution that contained a very specific concentration of urea and nitrate ions, and where the ratio of copper to zinc to aluminum was 5 to 2 to 1, and apparently, all of this was super important for how the final catalyst would turn out. I should say though that up until now, no reaction had happened yet, and to actually get things going, I was gonna have to heat it up. So that's what I did next by turning on the hot plate, and at the same time, I carefully watched it as the temperature slowly rose, and when it eventually got up to around 60 C, it didn't look like there was much of a difference. However, at least in theory, the urea should have been starting to break down into ammonia and CO2 gas, with the ammonia causing the solution to slowly get more and more basic. Then, as the solution continued heating up, the rate of urea breakdown was supposed to increase as well, and at least based on the amount of bubbling that I saw, that definitely seemed to be happening. What I thought was much more interesting though was that when it eventually got to 95 C, the solution started becoming cloudy, and this was because it was at this point that the catalyst was starting to form. More specifically, the metal nitrates that I'd added were now starting to be affected by the pH, which was causing them to slowly turn into various hydroxides and hydroxycarbonates that were no longer soluble in the water. This in turn was causing them to slowly precipitate together as a very intimate mixture of copper, zinc, and aluminum, and with a very specific ratio of 5 to 2 to 1, and at least so far, everything seemed to be going exactly as planned. But anyway, at this point, I basically just had to keep heating it like this for a couple of hours, which should have been enough time for pretty much all of the metals to get knocked out. During this time, the color also seemed to change quite a bit, which I assumed was good, and when it was eventually done, 2 hours later, I was pretty happy with how things were going. With the main reaction now done though, what I had to do next, according to the paper, was age it for 24 hours, and in my experience, this usually meant to just leave it how it was. However, at least based on what I'd seen in other similar procedures, that wasn't always the case, and what really didn't help was that there was absolutely no further information about any of this anywhere in the paper. So I kind of just ended up doing what I felt would work, and by that, I mean that I decided to leave it stirring, but to knock the temperature down to 65 C. I then just let it sit there, and over the next several hours, all I did was occasionally add water to it, and for the most part, it seemed like things were going okay, except for some reason, I just couldn't shake the feeling that I was doing something wrong. So, out of pure anxiety, I ended up reluctantly emailing the author again, which I really didn't want to do, because I had already pestered him with way too many questions. However, I'm glad that I did, because it turned out that everything that I was doing was totally wrong, and he basically told me to do the complete opposite. More specifically, I was apparently supposed to keep it at the same temperature of around 95°C, and I was supposed to completely stop the stirring, which he said was important for catalyst particle size. So apparently, everything that I decided to do was wrong, and now everything that I had in this beaker was just a bunch of trash, and this was pretty disappointing. But that's just kind of how it goes with chemistry sometimes, and what I did next was the only thing that I could do, which was just restart by first getting rid of this entire reaction. Then after that, I basically redid everything that I'd just done, except this time, after heating it for the 2 hours, I transferred the entire thing to my sous vide, which was normally meant to cook things like steaks. In this case though, I felt that it was perfect for what I had to do, and it should have had no problem holding the reaction at a near perfect 95°C. On top of that, with the lid,
Hi everyone, welcome to Go Classes. Maybe Lossy, the actual. Hi everyone, welcome to Go Classes. In this lecture, in this video, we will solve this GATE 2021 question. So this is a GATE 2021 question from DBMS subject. This is based on decomposition. So you have a relation, and this relation, in this relation, these are the functional dependencies, and two decompositions are given to you, D1, D2. These are the two decompositions given, and the question is asking which of these decomposition is lossless or lossy. Okay, you can notice that D1 comma D2, both of these are actually, I can say that these are actually non-binary. So this D1 comma D2, these are non-binary. This is also non-binary decomposition, because how many sub-relations we have here? So this is also non-binary decomposition, and this is also non-binary decomposition. You can notice in this D1, in this decomposition, we have total 4 relations. This is the mistake method. So remember, D2 decomposition, we have total 4 sub-relations. Okay, so in this situation, remember, don't apply the successive joining method. So this is the mistake that many students will do, that they will apply the successive joining method. Remember one thing, that successive joining method is not a reliable method. Okay, so if you get to the answer lossless, okay, so this successive joining method, so let me tell you again this point. We have already seen this point, and I have already given you one example where this successive joining method, this successive combining method, basically this will actually not work. This will fail. In some examples this will fail. So this successive combining method, this is a one-way method, you know. So this is only a one-way method. Hi everyone, welcome to composition is non-binary decomposition. Binary decomposition, I can say. Okay, that this condition, this checking, this testing, so this test will work only for binary decomposition, I can say. Okay, so you can notice that if this method says that answer is lossless, then answer will be lossless. But if this method says the answer is lossy, then answer may or may not be lossy. So remember this method, if this gives you answer lossless, so this method, if this method says that answer is lossless, if this method says answer is lossless, then remember, if this method will give you answer lossless, then remember the answer will be actually lossless. The actual answer will be lossless, I can say. The actual answer also will be lossless. But you can notice if this method gives you answer as lossy, if this method says that answer is lossy, then you can notice the actual answer may or may not be lossy. This actual answer may or may not be lossy. So this is the point. So that is the reason this is not a reliable method, may or may not be lossy. So remember this point, okay? So this successive combining method we will not apply, and whenever you have non-binary decomposition, always try to apply the Chase algorithm. So the Chase algorithm is the best algorithm that you can apply for this question. Okay, let's apply this algorithm. Okay, we will solve this D1 also D2 with the Chase algorithm. Okay, and Chase algorithm is actually very simple. It is time efficient. Okay, so it will save a lot of time if you apply the Chase algorithm, and this is very simple, and let's apply it. Okay, so this is D1. This is the set of functional dependencies that is given. Okay, now let's apply the Chase algorithm. So the Chase algorithm says that the columns will be created for these attributes. So if we have attributes P, Q, S, T, X, Y, Z, W. So okay, these are the columns P, Q, S, T, X, Y, Z, W. These are the columns. Now let's make it. Okay, so these are the columns that we have. Columns will correspond to the attributes, and the rows will correspond to the sub-relations. So you can notice total 4. We have total 4 sub-relations. So you can notice this R1, R2, R3, R4. These are the sub-relations that we have. Now let's see for D1. Okay, now you can notice in this decomposition, R1 has P, Q, S, T. So these are the entries. So let's make the entries. So P, Q, S, T, P, Q, S, T. These are the A entries. In this R2, we have PTX. So in this PTX, you can notice here P, here T, here X, and here again QY and YZW. So you can notice here you have QY and here you have YZW. So this will be YZW. Okay. So this is the initial setup. Okay. So this is what we have done. Now let's see what we can do further. Now you can notice here that P determines Y. Okay. So you can from here you can notice Y determines Z. Okay. So let's take this Y determines Z. So whenever Y value is same, you can notice in these two tuples Y value is same. So here in these two tuples Z value also will be same. So you will put Z here. You can notice Y determines W. Okay, just look at it here. Y determines W. So in these two tuples Y value is same. So in these two tuples Y, so in this QST. So okay, now you can notice in this decomposition R1 has PQST. So these are the entries. So in this R2 here X, and here again Q you have and YZW. You can notice this will be here PTX Z again. Now let's see what we can do further. Now you can notice here that P determines Y. Okay, so you can from here you can notice Y determines Z. Okay, so let's take this Y determines Z. So whenever Y value is same, you can notice in these two tuples Y value is same. So here in these two tuples Z value also will be same. So you will put Z here. You can notice Y determines W. Okay, just look at it here. Y determines W. So in these two tuples Y value is same. So in these two tuples W value will also be same. So you will put A here also. Okay, so this is the point. Now you can also see that now. So let's do this. Okay, so this is what we got here. So we got A here, we got A here. Okay, so these are the two entries we got. Now what else we can do? Okay, so after this you notice that again. So Q determines Y. Okay, so you can notice that Q determines Y. So in these two rows Q value is same. So in these two rows Y value will also be same. So we will put A here because Q determines Y. Okay, and you can notice P determines Y. Okay, now we can also see that P determines Y. Because P determines Y, so if two rows have same P value, then these two rows will also have same Y value. So you will put okay A here also. Okay, so this is what we got actually. Okay, so these two entries I can make it here. So these two entries you got now A. Okay, now what else we can do? Now from this what else we can do? So these two entries we got here A. These are the two entries we got. Okay, now from this you can notice that Y determines Z. Now you can notice again Y determines Z. So in these rows y value is same. So w can say that we can do here determines x. You can notice p determines x. Just take this p determines x. So in these two rows p value is same. So in these two rows x value will also be same. So just put a here. Okay, so now you can notice now what we got. Now you can notice this is what we got. So we got a row with all the a entries. So this is what we got. So this is what we get, that all the a entries. You can notice this is a row. This is a row with all a entries. With all a entries. So because we got a row with all a entries, so I can say this is a lossless decomposition. Okay, because we got this all the rows decomposition. So we'll have total. We will make the same to that. So can so there is no row with all a entries. With all a entries. So what you